going to share my screen. And just to verify, you guys can hear me and you can see my PowerPoint here. Is that correct?
Yep.
All right, thank you. Here we go. We're moving into to our last topic and our last lab prior to our capstone. So I'll review that a little bit as well. All right, and so welcome. We're going to basically be going through the variable frequency drive. I got most people's labs in. Peter was going to get me his. And I think all the homework is in. We're done with that. So here's the schedule. Just want to be sure that we're good on this. We're going to do the VFD lecture, and we'll have our quiz tonight afterwards, our analog quiz. And then we'll have our lab coming up. And some people are getting close on that. It's a little bit of a doozy because it uses sequencers again in there, and we'll explain it. And then we're going to start our capstone. Now, remember, we lost a lot of time, so we're just going to kind of jump right into this capstone on this 4/18, which is a Tuesday. So next Tuesday, instead of WebEx and lecture and all that, we'll come into class at LCC, and we'll get going on the capstone. How about, I'm thinking like 6 to 8, you can get your equipment. You can figure out, what you're doing. We can sort the equipment and get you all situated. You can get started if you want to. We're going to do teams. We got 14, so I'm thinking 2 teams of 3 people and 2 teams of 4 people. So start thinking about who you want to be on your team for the capstone, okay? So 3, 3. I don't think we can do it any other way. I don't really want to do a team of 2. So that'll give us 4 teams, 3, 3, 4, 4. We have a quiz that night over analog as well, all right? And so if you're going to get started here, I have a few limited amount of tools. If you have some tools, which are just going to be like strippers, screwdrivers, basically stuff like that, a tool kit, you should bring that to the capstone. I think it will be key for that. And then basically we'll be in. So I'm thinking, once again, 4:20 on the capstone here. We'll talk about it, but I'm thinking I'll probably be there from 5 till 9 p.m. And then we'll just keep, this here probably 5 to 9 p.m. on each one of these from here on out. All right, starting on, from here on out, we're going to be face to face. All right, working the capstone. Bring your tools. Let's see what else I got about that capstone. When you're done with it, because you might be able to work through it pretty fast, and divide it up and be sure everybody understands what's going on and get it programmed and running and everything like that. When you're done and it runs and I have all your paperwork, you can tear it down. So I've got the last day of 5/4 is the tear down, but if you get it done on 5/2, you can tear it down. At that point, I'll open up the final exam for you and you can take the final exam. So the final exam, there is going to be a study guide. Let's just be sure that I'm not lying to you. Final exam review. Yeah, if you go to final exam review, there's some example questions. Once again, you kind of want to go through and just look and kind of get an idea, between these two things of some of the things that are going to be on the final, the flavor of it. Okay, so that's where we're at. We're at home stretch. We're going to finish this lab, and then we're going to start our capstone. And it's 1, 2, 3, 4, 5 times 4 is 20 times 60 to 80 man-woman hours to get this done. All right, and I think you can get it done. And so, and we'll go over and be sure you understand it coming up. The final, I'll open it up on D2L at home. Yep, it'll be timed though, so you'll either go through it in a timely manner and do well, or you won't. But I think that we've really been through a lot the last year, or over the course of these 2 PLC classes and the machine controls, that you'll be okay. All right, so for the capstone, for your tools, you would, the things are screwdrivers, whether you have, Phillips or standard and different sizes, wire strippers, Allen wrenches, things like that, are what is kind of popular, just to put it together. Yeah, you're basic, or you're at work and you got a basic toolkit, things like that. So that's where we're at with that. Okay, so the schedule. Everybody feel yes or no? Do they understand the schedule? How about some yeses? Everybody got a yes? They feel good about the schedule? And your teams, you'll figure it out, and then we'll be ready to go here. All right, wonderful. It'll be good. And another thing that we have to figure out is, who can drive and pick up the pizza? All right, because I ordered the pizza, but I don't want to leave, so we'll have to get a driver. It's like 7 minutes away to go and pick up the pizza. So that's pretty critical, because what we'll do is we'll be working down in the big CME room. I'll put you at a table, you can spread out, and you'll have your units and everything down there. All right, so that's how that goes. But we got to get somebody to pick up the pizza. All right, let's talk about our lab review. So it did seem to go reasonably well. It got a little complicated at the end. Maybe the one thing was that channel 0 is 0 and channel 1 is 1. So when people were going in their card and setting it up, going their card set up here, there's a 0 and a 1. We were using these two. And if you set up 1, but then in your program, we're using channel 0, then you have to have the channel corresponding to, whatever you programmed. And so I think some people were struggling with that a little bit. Hopefully it made sense. Dint or real. All these numbers were real. I wanted you to keep the decimal point. So some people were making dents, and I said, yeah, change it back to real. I don't want to truncate anything. So you were taking a real number, for example, and if you were moving it to a storage 1, for example, which is a dint, what happens? Well, if it's 162.32, it truncates it. It becomes 162. It takes it down to the to an integer. All right, then no decimals. So we wanted a real going to a real, and then you try and move a dint to an analog output. Things aren't working like you want them to. These need to be reals because that's what this is reading. Same thing if you move an int and do a dint, you can do these things, but if your number is bigger than 32,767, and you went from a dint to an int, it truncated, and moving into a dint, that's probably not going to matter if you move an int to a dint, because a dint is a much larger number, a double integer, than int. Okay, so hopefully that makes sense. That if you move, I guess, to a lower level, whether you're moving from a real number that has decimals to an integer that doesn't, to a smaller number of bits, you truncate the things that particular data type can't tolerate. Does that make sense on a scale of 1 to 10, of how the data types work there when you accidentally mix and match them? Oh, Joanne, you made it. Wonderful. Joanne, how was your drive? Was it yucky? I'm just kind of curious.
It was a little rough getting out of there. Then at one point in time, I looked down and I was going 90, so I figured I better slow down. So,
there you go.
But there was a traffic jam there for a minute.
All right. Well, everybody, Joanne, I'm going to tell, had FANUC training in Rochester. So if you get trained on the FANUCs, your company might send you to Rochester. Has anybody been sent over there to get training yet on FANUC from their company? Anybody sent locally? No? A lot of times, that's where they would send you. And it's just, oh, Robert Young, I will next month. There you go. Well, it is yucky over there, driving over there. It is crappy, man. The highways, and there's so much. I live in Brighton, so I actually got to go down 696 and all that. That's really bad, whereas you're going to come the other way. Woo! Not good. But if you take the METS 160 class, you would get all of that FANUC operations anyway, so I wouldn't think you'd need it.
It goes into a little bit more in depth, but because I'm taking a 4-day class, so it goes in a little more in depth, but it's really fast at you.
That's the thing with that training, and we're deviating, I know, but it's 32 hours. And man, it's going to be hard to remember any of that unless you're using a robot a lot. Whereas if you take the training here, you take METS 160 or METS 260 here, you get the robot twice a week, you get that teach pendant in your hand, and you're moving around, and even though it's a slower pace, it probably might sit in your brain a little bit better, just because it's any kind of corporate training you do. If you go and take an Alan Bradley class for PLCs or something like that, they're going to just bombard you with stuff, and you're going to walk out of there, and it's going to, in my opinion, going to be hard to understand or remember that stuff unless you're using it. So that's the way corporate training goes.
True.
But if you've had this class, I'm going to say that you're going to do really well at any corporate training, because I've really beat you over the head. You heard it here first. When you take corporate training from now on about PLCs, you're going to be way ahead of the class. Anyways, we got our scaling discussion of our card setup, and I want to be sure everybody understands this. So this is local I. So this is the input card. And remember, the input card reads 0 to 10 volts. All right, it's going to take 0 to 10 volts in, and I've got showing right here voltage in 0 to 10. Now, it's not made to take in more volts than that. You want to have something variable that's going to take in 0 to 10. You don't have to use all the way up to 10. You don't have to use all the way down to 0. You could have something that's reading between 3 volts and 8 volts, but between 3 and 8, that fits in between 0 and 10. So we're all good with that, okay? There's different ranges here. You can go 10 to minus 10, 0 to 5, whatever, but we had 0 to 10 volts is what our input range was. So here was my scaling. I was taking in 0 to 10, but I was only using 1 to 5. All right. So if I look at my item here, I was only using 1 to 5. I could go more than 6, 7, 8, 9, 10. I can go more, but for some reason, I don't want to use 6, 7, 8, 9, 10. I only want to use up to 5 volts. And so maybe that's what my sensor says. You're supposed to, input between 1 and 5. And that's the way you would wire it up. It could go more, but it might not be accurate at 6 or 7 or 8 volts. And so we set our low and our high engineering. And what this does is it makes 1 volt. If it reads 1 volt, it'll return 32 degrees. In this case, if it reads 5 volts, it'll return 212 degrees. But remember, these don't have to be degrees. These could be RPMs or something. All right, 1 volt returning 32 RPMs or whatever. So if I returned 3 volts somewhere in the middle, well, it's going to be a number here in the middle, okay? And if I return 6 volts, it's going to be higher than 212. But once again, because our scale is 1 to 5, we probably don't want to use that voltage because it might be, the sensor might not be accurate there, okay? So according to that, I was reading from 1 to 5 volts, and I was getting a converted temperature right here from between 32 and 212 degrees. It was supposed to be accurate, okay? The converted temperature here from voltage to temperature, I don't do anything except set the card up. The card does all the math for me. Okay, so if I get 2.34 volts, it somehow is returning, some value in here of 55 degrees. I don't know, whatever it is. And then 55 degrees would be here. All right. So let's look at the voltage out. You could set up the voltage out. I had you take the temperature and convert back to voltage out. What you could have said was, hey, I could have said, pretend this was my output card. All right, pretend this was my analog output card, not my input card, my analog output card. And I could have did my scaling 32 to 212, push out to my output card 1 to 5. Okay, does that make sense what I just said? Yes or no? Just one yes? Okay, so if it does, then when I turn this up to 1 volt right here, if I turn, where was that 1 to 5 again? It's right here. I said I'm using on my input card, I'm taking in 1 volt and equals 32, and my input 5 volts is 212. But if I would have set my output card out instead of my input, and I would have said my output card, 32 degrees to 212 degrees equals 1 volt to 5 volts. So I'm basically taking that, you know, in trying to move it back, you know, that the output card looks a little bit different here than the way that this does. You still have to set it up, but you can kind of do the same thing here, just reverse between your high and your low engineering. Okay, that's the way the output card would work. So here, all right, ready? I'm going to ask you, if I turn my voltage up right here, my input to 5 volts, everybody, what temperature pops up here again, everybody? What temperature pops up here? 212. That's right, 212, because it's set my input card to do 212. So then if I set my output card and said, hey, 212 degrees means 5 volts, then I would be getting, it would take this right here, and it would take the 212 and it would push this right here to 5 volts. All right. But here's the thing. Ready for this? The 5 volts here that's being pushed out isn't the same volts that's coming in. The voltage that's coming in is an input voltage, and the output that's going out is voltage that is produced by the output card. So if you would have just set your output card to like read the voltage out, it'd be close. Probably would be close. You'd think it would be close. But the input voltage, if this is if this is 4.99 volts, let's say, the output voltage here isn't necessarily 4.9, because there's probably going to be some calibration errors between the way the output module is working and the input module is working. Okay. And as a matter of fact, you can screw the output up, because when you go and set the output up here, you could change your engineering instead of what we use for the input. You could have changed this from 22 to 170, something like that. At which point then whatever you're getting out might be a bunch of garbage. All right. But it is still pushing out output voltage. But whether you're taking in input voltage or pushing out output voltage, you got to give it the range of what it equates to. All right. So once again, this is the input screen, and that's, just talking about input output. How do you feel on a scale of 1 to 10 about the way that this scaling, this range thing is working here? Scale of 1 to 10. How do you feel about the way the range works? Yeah. Okay. And so just to reiterate, I mean, life is good when you say, all right, I want 0 volts, 10 volts, 0 degrees, 100 degrees. Man, that is just nice. So if my card reads in 5 volts, I got 50 degrees. Woo! I'm really good at math, right? Well, it's not just that. The card does do all this for you and scales it all. It's when, these aren't super nice numbers that are divisible into each other that the math becomes a lot more. But the card does all that for you. It creates that y equals mx plus b, so that if you want to solve for y, you just put x in there, and then it'll solve your value for you as you go. All right, that's what that card is doing, and it's good. Okay. So our alarm configuration, you had to do a little math there. We had some crazy numbers going on here, but these were the numbers for my alarm configuration, because we had 1 to 5. Okay, 1 to 5. Let me just draw that out again. Oh, it's right here. Sorry. It was 1 volt, 5 volts, 32 degrees, 212 degrees. And then it asks you for 0.85 volts and 0.75 volts. And I think it was 5.15 volts and 5.25 volts. Okay. Well, 0.85 is less than 1. So this has to be less than 32 degrees. And this has to be even less than that. And this has to be more than 212 degrees. And this has to be even more than that. Yes or no? Does that make sense, everybody? Yes or no? When I draw it out, okay. Then you wanted your high and your lows. But it didn't ask for the voltage because that's not the way the card works. The card, we gave it the range right here. Whatever we gave it here, we gave it, once again, 1 and 5, 32 and 212, and it did that for us. Well, then all we got to do is, plug this into here, and it will return that value. It'll solve it for us. It's got the equation of the line. So when you ran that math, it was 20.7, 25.25. It was 20.75, 25.25. Those were the values that you got for the high and the low. All right. But once again, the card did it for you, and you had to do it yourself. And it was like, God, I don't like this math. Some of you like the math better than the others, but because it was 1 and 5 and 20, 32 and 21, you just couldn't cross multiply. Whereas here, if I gave you 0.43 volts to X, that's where you could say that 10 volts is to 100 degrees, as 4.3 volts is to X, and that's where you just cross multiplied and solved. Yeah, when it's all ratioed out equally, it works. But when things don't start at 0, that doesn't work. All right, and that's why we had to do the math there. So we went and we set those up. Calculations, we did add, multiply, divide, or you could have just did a compute. A compute could have been your expression right here. In a compute, you can put, multiplications and multiplications, divisions, everything into a compute. You can type out a really long, nasty formula in a compute if you want, and then put that into a destination. Did anybody use the compute, or did everybody just use add, multiply, and divide? Everybody's used add, multiply, and divide? Yeah, the compute's just for formulas, all right? Yeah, add, multiply, and divide. Okay, yeah. And they could be in series or parallel. Some people put everything on, like here's one, or I just kept it simple, subtract. This was my rate, and this was that, and this was that, and I put them in parallel. Some people put this on its own rung, this on its own rung, this on its own rung. You could do it that way. That's fine. Or you could take all of this. See this rate equals scaled max minus scaled mod divided by input max. You could have just put that in the CPT, put it all into the expression down there, and it would have done it for you. Okay, that would have worked too. And we did the add-on instructions. That was similar to a function block. So we were doing F to C. Remember, you're taking something in, engineered in, voltage out, or whatever. This should have said, I guess, engineered. Probably should have said Celsius out. I think I messed that up. Celsius out. But you got to make those visible. You're taking in some value, and we're outputting some value. And this creates y equals mx plus b, the slope of the line for these two numbers compared to these two numbers. All right, which is exactly what the card did. We just went in the reverse. And I said, if you wanted to set your output card up, the output card's kind of just doing this. This scale with parameters is kind of a standard instruction that you would want to use in future, because you might have some ratios on something. You're mixing something and you need voltage, and the ratio of your mixture needs to be a ratio of voltages, or the ratio of a recipe needs to be the ratio of the voltage, or the ratio of your voltage needs to be the ratio of a recipe, or something like that. If you need to ratio two numbers to each other to get y equals mx plus b, scale with parameters is the way to do it. All right. Like I said, you set this up and you had parameters, and then you had local tags, okay? And you wanted your parameters here to be visible so that I could actually enter these. So it looked a little bit like a function block, all right? So how do you feel about the add-on? It's called add-on instruction. Scale of 1 to 10, how do you feel about the add-on instruction, about creating one? So when you get out programming, if you're doing a lot of programming, or you get into a lot of programming or see a lot of programming, you're going to see add-on instructions all over the place because it's the code that somebody put together. They just want to reuse over and over and over again. They don't want to recreate this code every time. They're going to put it into an add-on instruction. They're going to drag that add instruction in, and then they don't have to recode it. Okay. One of the things you might see is an add-on instruction would be IO mapping. Some people do it, they're mapping with that. And what they do is they put this right here, and it might say input map, okay? And it might here say input. And your input might be, you know, local 2.I. So you put your local 2 wherever your input, that's where your inputs are, local 2. Then it would map them. What would the logic inside of here look like? It would be, you know, 2.0 is PB1, or, you know, 2.1 is PB2, or whatever you want to call these, you know, 2.2 is PB3. And so you just drag this in and you put your whatever module you got there, and then bang, it's all mapped. All right, this might not PB1, 2, and 3 might not be the best way to do it, but you could tie this in, because if you have another set of inputs, just drag that input map AOI in, and then bang, you just put one thing, and then you don't got to program that because it's kind of redundant. All right, so that's, you know, one way that people might do input mapping, might do it with an add-on instruction. All right. Quiz review. It's kind of tough material, but I have a quiz here. So this was sequencers. You're going to have a sequencer in your in the drive, one coming up. So I want you to be sure to do it. A PLC sequencer advances through its steps. Information is transferred from the word file to the output word. So you're taking a group of words and you're pushing them out to an output. Okay, and you can push them out to an output module. Turn on lights. What we're going to be doing is we're going to take the output word, we're going to push it out to a variable frequency drive. All right. Sequencers, the SQO instruction shown, the destination is the address output, which is the sequence to move the data. That's my destination. Where is it going? Is it going to the output module? A lot of times you're turning on outputs, but in this case, we're sending it to the VFD. The sequencer shown below, the file is the starting address of the registers that contain the data to be transferred. So we're going to have a bunch of registers that we're going to cycle through. A single sequencer instruction may have an upper limit on the number of steps that can be programmed, the number of external outputs that can be programmed. Certainly, yeah, you have to be limited by your hardware. As the output advantage of steps, the data is transferred from the sequencer file to the output card. That's right, it's going from this to the card. When the SQI is paired, is illustrated, the same address, length, and position values used. Yes, they got to be the same because they're going to have the same control. It's indexed by the sequencer. Remember, the sequencer is the indexer. That's what causes the position to go. It allows input-output sequence to work in unison. Yes. And this is what is depicted as hexadecimal. It would be 0000000, and then these would be FFF. So that's what I got right there. It's only a 16-bit word, so really it was only using this right here. So if you would have given me 00FF, that I had taken that, because that's really what it is, 00FF. All these other zeros here, I probably should have had 16 more zeros out here, okay? The value of the new destination word, here is my source. So was my source going to stay the same? Or was it going to replace this current? Or was the current going to stay the same? Well, it's going to be a mix of the mask. So the 1 lets the new one through. So for example, here was a 0, but the mask let the 1 here to come through. So the 1 went through and it became a 1. Okay. Here the mask was a 0. So this 1 wasn't allowed to come through and replace that one. So that's how that mask worked. How are we feeling about masking, everybody, on a scale of 1 to 10 when we're doing a word shift? Okay. Yeah, sometimes you don't, sometimes you want to replace it, sometimes you don't. All right, so that was kind of the gist of the quiz. All right, pretty short lecture again tonight. I just want to touch on variable frequency drives. If you want to change the speed of a DC motor, you change the voltage. You turn the voltage up and down DC, change the voltage, it goes faster or slower. You want to change the speed of an AC motor, you have to change the frequency of it, which is a little more difficult because the frequency that's generated in the US here is 60 cycles per second, 60 hertz. So how do you change the frequency that you're working with, okay? And that's what a frequency drive does. It changes frequency. And we'll talk about, I say question mark, because it's working with the frequency that's in the line. It incorporates motor starting functions, incorporates safety relay functions. So VFD can have all of those. So who has had 232 already and already did some talk about variable frequency drives? Matt did. Anybody else had 232? Okay, Matt, yeah, okay. So you've already done some VFDs, and you've done some soft starting already. Here's a soft starting lab, okay? And so remember, when you're doing a soft start, there's two types of connections here. One is called a Y, and the other is called a delta. And you can put those loads in kind of a series here, or you can put them in parallel right there, all right? And so when you do this soft starting, you'll notice that when these contacts are closed, the right side of this coil is hooked to the right side of this coil is hooked to the right side of this coil. Those coils are all connected on one end, and I'm thinking that that looks like this, okay? And then when this starts, this SR closes, 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 and this opens, opens, opens. So now I've got this coil in series with this coil in series with this coil. And it looks to me like I got this one in series with this one in series with this one in series. I got a delta, okay? And so what this is used for is a soft start, that when I start, I'm going to start on the Y, okay? And the purpose is to, watch the ampacity that's driven, because we've talked about when we start and we have inrush current, where we have time and we have current, we get a spike coming up here. And then when it starts coming steady state, it starts leveling off, right? And so we might start it on the Y and get it running up to speed a little bit. And then we might switch it over and hit it up again like this with a delta. And then we might end up with our steady state current up here. Versus if we would have hit this right away just with a delta like this, it might have just popped the circuit breaker completely. It might have just, the inrush might have just been too much, and it might have popped the circuit breaker. So that's called a soft start, okay? Now this circuit here is what you built in 232. We got a lot of problems with it. You're in a race here because you got an SR contact here that's closed and an SR contact here that's open, and an SR relay here. So when this relay hits, these close and this opens. Well, you definitely want to be sure that these open before these close, all right? So using the same relay for that, we did that as a homework assignment where we put a timer in there. We had two different relays here where these were on, these opening ones opened, causing a timer to go on the PLC, which then closed these. So there was no accidental closing of these at the same time, all right? And the same thing here, that's a problem with these relay. It works, but sometimes you get into a little bit of a race. And we talked about it earlier with the garage door opening, when we did converting ladder logic, that when this SR comes on, you know, this is closing and these are closing. What's another one? Oh, the motor starter here, motor open. Oh, my time relay. So I got my time relay here. These are opening and this is closing. So you got multiple sets of contacts on the same relay, some opening and some closing at the same time, that you want to be sure that you don't get any trouble with here. And this control relay has to hold here before this opens, and you know, sometimes you have to hit the button twice to be sure everything clicks and where it should. We did this for homework assignment with a PLC with a timer, so there's just a little bit of time, not very much, just a little bit, but all these close, you know, not all at once, but you know, this happens and this closes and this closes and this closes very rapidly, but you know, the time domain's a little bit different on this one. VFD architecture. If you had 232, went over all of this. I'm not gonna knock myself out or knock you out talking about these. The thing when you go to size a VFD, or work on a VFD, variable frequency drive. And by the way, does anybody work on or seen variable frequency drives at work? You guys see VFDs at work? Yes. Okay. Yes. Yeah. No, not for you, Router. Huh? Okay. So you can still start a motor with a memory circuit and a motor starter in overload. You can. It works. But the VFD is a really good way to go for all the reasons that I mentioned, because it can do the soft start for you. If you need to have some soft start involved in that, you don't need to get crazy with, you know, multiple starters here and multiple relays and time relays. The VFD does it for you. It's all one unit. If you want to put in a safety relay in here, we already went over safety relays. The safety relay here would bring down my motor starter so that we would bring these contacts. So the safety relay would be, there'd be a set of safety relay contacts right here, and then a whole separate safety relay that had its own wiring, the purpose of to open up the contacts here. You don't need that. We're not doing it, but our safety relay, our guard logic safety relays, they have in there dual channel contacts that if we wanted to incorporate the safety function of it, the dual channel safety, they're already in there, and it can shut itself down with a dual channel e-stop. It's got its own safety relay built into it. So yeah, it's safer because we could wire this up and add a safety relay to it. But this is starting to get pretty expensive, you know, with all these parts, probably more expensive than a VFD. And then, so we got a soft start. And then there's also some hybrid starting capabilities of the VFD, because this motor starter right here, these contacts open and close. You know, you're turning this motor on, open, on, off, on, off, on, off, on, off. Somebody tell me what happens to these contacts right here when you turn this motor on and off like 500 times? They wear out. Yeah, they melt, they pot. You got to change them out. You got to service them like that, right? Well, a VFD isn't going to have that. A VFD is going to have a hybrid parallel start that we already talked about, where it's going to have solid state contacts close, and solid state contacts don't have any moving parts. So the solid state contacts turn on. That starts the motor. And once the motor's running, then the real contacts close, and there's no spark at that moment because there's already a parallel path. And then the solid state contacts open, okay? And so if I wanted to draw that real quick, just to be sure you understand the hybrid starter, you're gonna have a solid state contact here, right? And then you're gonna have a parallel contact here. So the solid state closes. I got current coming here to the motor. This then closes, so now I got two paths for current. No spark, because I'm really not passing current through it. All the current's coming through here. And then open this up. So now the current comes through this contact. And there's no pitting on it because when it closed, there was no spark. Same thing when you shut it off. Close this. let the current have this path, open this, and then open that. All right, that's the way your hybrid starter would work. And that's all built into a variable frequency drive. All these motor starting functions are built into the VFD. And once again, I want to tell you that the VFD is probably non-serviceable depending on how big it is. So the people who responded, they work with VFDs at work. Do you guys try and fix them when one blows up? Tell me what happens on that. Or do you just put a new one in? You be able to fix VFDs? You just replace. Yeah, they're hard to fix, man. You can send them out. If it's a really big, expensive one, they might take a look at it. But you can just buy a new one and just put it in and program it, and bang, it's ready to go. All right. Certainly, if something goes wrong here, you can take it out and then put in a new component, which one of these components you want. You certainly can, and you could get this working. But remember, all of this functionality is going to be in a VFD. And another thing about VFDs is they can be very big. Like there might be a limit to them. Man, I don't know, man. My brother Scott works is a plant manager in a chemical facility, and they got maybe 500 horsepower motors, and they got VFDs on them. So they do go very, very large, but they do get very, very expensive. But the motors that they use cost $500,000. So if you can put a $50,000 VFD on it and you can protect that motor, it's probably a good investment. All right. So when you're talking about the VFDs, and they're popular, like if you're a hobbyist, they got all these hobbyists that turn all these bowls and stuff. Someday when you get old like me, you're going to retire and you're going to put a wood shop in your garage or something. I guess that's what people do. And then they turn bowls on lathes and they make stuff. And they want variable speed. And so they buy these little VFDs that are like third horsepower, half horsepower. So these VFDs are all over the place. And I sell automation equipment. I sell tons of VFDs, all these little ones, all the way up to big ones. But it does depend on what you want to do to determine the type of architecture that you want. And I'm not going to go all the way into this. I think Sherry went over a lot of this with you guys already. You guys already been over this a lot with Sherry, right? For 232, those that have taken it, is that right? Yes? Okay. The moral of my story is that if you're at the point in your company where you're selecting the VFD that you're going to be using for the operation based on whatever horsepower, then you're going to have to do some reading. You're not going to be able to go back and remember everything that I could teach you, that Sherry could teach you. You're going to know that there's pulse width modulation, current source inverters, or voltage source inverter. That's what you're going to know. All right. And you're going to say, oh, I remember this. I got to start reading for a few hours to come up with what I need to do. All right. And so it says, what is a variable frequency drive? And those were the ones there. And here's another one, best VFD topology. And there's even more. There's cycle converter, load commuter inverter, VSI. There's a lot of different things that you would go depending on how big of an inverter you want. And these are for big ones, all right? But that little link that I gave you, if you want to read it, I'm not going to go all the way. It's just going to tell you that the standard three-phase has a converter, a filter, and an inverter. All right, AC to DC. That's what they're going to do. And then an inverter section here. They're going to take the DC and make it to AC again. All right. So that is the standard three-phase VFD. All of them are going to have that. All right. And the rectification section, the filter section, the switching section. And so if you look, and we'll go over it, the rectifier is going to use a diode bridge. And so we've talked about a diode bridge in this class, and you would have talked about a diode bridge if you had 136 or maybe you had 232. Have you guys talked about diode bridges in any of your other classes? I think we might have talked about it in 131. Diode bridge, you guys familiar with a diode bridge? Okay. A diode bridge, a diode only allows electricity to pass one way. So when this red right here is coming up to AC positive, it allows electricity to pass. But when it goes negative between the two, electricity cannot flow back this way to it. It's blocked by that gate there. And then when the AC comes high again, it allows it to pass. So it allows only electricity to pass one way. Well, when you bridge these, when you put a bridge in there, or you put these diodes in correctly, what you do is you can make DC, because it comes up and you get the current, and then it can't go the other way. I'll show you another picture of that, all right? But it's the kind of the rectification. Then you got a filter here. You got a filtering capacitor, and I'll go over that again. And that's to smooth your new DC out, all right? And then you got your switching or your inverted. So you're gonna bridge higher. I'll show you. I'm gonna draw you some pictures. And there's some handouts in your thing that I'll go over real quick. And if it doesn't make sense, you can ask me. All right, Roderick. And then you got your inverter, where you got a bunch of switches here that are gonna flip on and off here to allow the current to flow to your three-phase here. Okay. So, and once again, these VFDs, and that's a good point. These VFDs are going to be for three-phase. We're doing three-phase here. All right. So here's my different types. VSI, voltage source inverter. This is the most common type of variable frequency drive. It's a diode bridge used to convert AC and its capacitor is used to store the energy. All right. So voltage source inverter, very, very common. Here's my advantages and my disadvantages. Like I said, if you get into where you're speccing out a VFD, you're going to go through all this, and you're going to talk to your manufacturers and see what's going on depending on the size. But if you're just doing a very small drive, 5 horsepower, something like that, you're going right here with this baby right here, voltage source inverter. Here's a current source inverter. I don't see these as much, all right? But once again, the VFD acts like a constant current generator. This is a constant current generator. Instead of a square wave voltage, is capable of providing a square wave current. We'll go over it some more. I'm not going to dive all the way into this one. This one's a little more complicated, the way the current source inverter works. And then pulse width modulation is another common one. An additional regulator is used to regulate the pulse width modulation, provide a stable and proper voltage. So this is going to be an improved and modified version of the VSI, okay, which is your which we said was the most common, the voltage source inverter. And that's really what we're looking at here, is the pulse width modulation. It's fancier, okay? And the better these get, and the more they're out there, it's like anything, the price goes down and down and down, and they're affordable, and you want all the bells and whistles with them. So this document here kind of explains it. There's a good explanation there of some of those things. All right. So those are our options: a rectifier, filter, switching, inverter, and I just want to review them. So I've got some handouts here that we'll go through. But let's talk about root mean square voltage. Scale of 1 to 10. Do you understand it? Have you heard about it? RMS voltage. You understand RMS? All right. RMS, I'll go real quick. The amount of AC power that produces the same heating as a DC. So this goes plus and minus, plus and minus. And so inside of this curve, and it down here and up here, all this blue here is where you can do work. That's your work, right? Well, what about the corners here? Well, if you do DC, it's just constant. Well, you actually get the corners here that you can do some work too. But if you took the corner here and the corner here, and you colored it in right here, it would fill up perfectly to this blue. So it's the equivalent voltage. So when your meter, your RMS meter, reads 115 volts AC, that's not the peak voltage. That is, the peak voltage is 170 volts. All right. So you guys have learned that quite a bit. All right. And so why do we need to know that? We need to know that because, once again, this is a handout. You got it. And this talks about how it's going. So we got 480 volts coming in. We got 480 volts, 3-phase on this VFD. And it is alternating. There's my 3-phase volts there, 3 legs. They're 120 degrees out. And we just want to pass A to B, A to C, and B to C through this diode bridge. And remember, it can only go out one way, it can't go back the other. And so what happens is when this blue is coming up, it can't pass back down, and so it basically truncates it here because we're only taking the highs of the voltage here, okay? And so we're only taking, this peak voltage here, because remember, this peak voltage up here is high, all right? And so what this right here is just a blow up of this. Notice the frequency looks a little bit higher, but the top of this is 680, and then the bottom down here has been truncated here at about 590. All right, so this is just a higher frequency of this. So we've got our very high frequency voltage now because of the bridge. The bridge is given this, all right? And then what we do is we put, like I said, that was next thing, is that we have our filtering. Okay, so we got our very high voltage, and then we're gonna do our filtering here, and we're gonna put a capacitor in here. So every time this voltage comes up, it charges that capacitor. And then when that voltage comes down, the capacitor discharges, okay? And so what you get is, I'll draw it here again real quick, sorry. If you were looking at a single instance of this, what happens is, this comes up, and at the same time while it's coming up, it charges capacitor. And then when it starts coming down, the capacitor then discharges a little bit, okay? And then so when this comes back up and it would come back here, it would then charge it up again, and then it would start coming down again when this fell. So you end up with this pretty flat DC looking voltage line right there, okay? That's what's showing here. That the capacitor is going to take this AC and it's going to make it just a flat line here, and it's going to be at our bus voltage of 650 to 680 volts. All right. So you think, well, the RMS is 480. Yep, it is 480, but we're just taking the high side. So we're actually now using some very high voltage on this bus. All right. And then what we do, we have the inverter. So now we're going to open and close these switches here. And notice this first switch runs to the motor phase 1, the second bit to the next motor, the next one to the motor, and then there's the return so that we can open and close these in sequence to allow the voltage to maybe flow this way, and then it could flow to there, and then we would let it flow straight to this one and around this way. So then we generate AC voltage by you want the capacitor to charge. Yeah, it's similar to the battery. Yep. And so instead of having all these lines up and down, as it starts to come down, the battery or the capacitor discharges and it makes it flat. Yeah. So that's what the purpose of that capacitor is. And then, like I said, you then move these switching mechanisms. They're showing the switches here, but these solid state transistors moving rapidly, and you would get AC voltage, or you get something that looks like this. All right. And so what you have is how long and how you keep those closed allows you to simulate your AC curve here. It's a square curve. It's called square because it's not smooth. You could get a pulse width modulation that we talked about just a minute ago. That was our pulse width modulation. This is an improved and modified version. Using that, are capable to provide stable voltage out with the frequency ratio. They use a diode bridge to rectify the AC signal into DC signal. So this adds a little bit more here in order to do that, to take that square wave and smooth it out even more. Okay. And then so once again, if you keep this on longer here and you pulse it longer here, whatever switches you go, faster, longer, you can get 480 volt 60 hertz, because you're pulsing the 650 volts, and then once again you're talking about RMS you're going to, because you're not using the outsides of this, you're looking at about 480 RMS. And so your 650 gets pulsed differently here. You don't pulse it as long, as frequently. And then this wave comes down a little bit. It's 240 volts, 30 hertz. Or if you could pulse it, real short here, 80 volts, and it would come across as being 10 hertz. This wave is not moving as much. So this talks about why I should use VFD, but this is, kind of the gist of using, so you would have pulse with modulation on his to make it even smoother, right? So how did my explanation go? Is that just a review for everybody about how the VFD works here? Does it make sense? Yes or no? What do you think? Yeah? Just basic, you'll be able to talk a good game. If somebody asks you how VFD works, you can say, you can give them a brief explanation, you think? I hope, right? Like if I ask you on a quiz, roughly how the VFD works, you're all over it, right? Okay, I hope so. The 3 parts and what each one does. All right, so that was my thing on the VFD. All right, finally then, you're going to be using connected components. So you ready for this? I'm going to ask you if you understand this. The lab that you have in your packet is using a firmware that's not working with the new Windows 11 computers. So I switched it over to completely setting it up with connected components. And I was working fast. Robert was ahead of me, so we were making it up as we went. The new lab is sitting on the desk in the classroom if for some reason you get there before me. So does everybody understand, a yes or no, that don't use the lab in your packet or you're going to be frustrated? Use the lab that's on the desk. Yes or no? All right, not a yes. I want to sit there. It's like, Sean, I've been sitting here for 3 hours waiting for this to load up on the computer. I know it's not compatible with the Windows 11. I think the lab on the desk will work. Okay. It's also on D2L. The lab has also been uploaded on D2L, but it's sitting on the desk. Do not use the one that's in your packet. All right. So that lab, I guess I'll pull it up. Why not? Where is it? Here. Just so you know, I'm not. Here's my VFD. Here's my where right here. So the thing is, here is where you're going to go, and you're going to set your power flex up. And a good way to do it is with connected components. Now, these VFDs likely have a static IP address in them anyway. So you're going to plug an Ethernet cable into your switch and be sure you see them. If they didn't have it, and they might not, they will be set to dynamic host protocol instead of static, right? There'll be DHCP. And so when you go in to set the address, it will dynamically find it, and then you can assign it 192.168.1 dot whatever. But if they coming up on links, that's good. Somebody already unclicked dynamic and clicked static, and it's done for you. So my next question. When you have something that does not have static IP, overall generally, do you know it won't work for you? Do you know that it's set up to be dynamically recognized by your computer? And when it's dynamically recognized by your computer, you can then assign a static to it, and then it would work. And there's that whole general process there of getting something from dynamic to static. How are you guys doing on that understanding that on a scale of 1 to 10? Dynamic versus static IPs. I mean, it's a lot out there. You just have to mess with some stuff. Boot P is another way to do it. We talked about Boot P of how to set stuff up. We'll probably have to use Boot P in this lab. Because for some reason when you're doing, or in the capstone, you'll be doing something and your Ethernet IP will lose its IP, or your drive will use its IP. You'll lose your IP. And then we got going through Boot P and set it from a dynamic host protocol to a static protocol. Okay. But going through connected components, and so here we go again. Yeah, I know. The whole networking thing is that IT/OT convergence that we talked about. That well, if you can't, that IT/OT, that if you can't, if you can't get anything talking to each other, it doesn't matter what you know. You need to have the hardware end of it, and you need to understand the IT. And the big thing that we did here was I opened my network and internet sharing, and I go to network sharing center, take it, change adapter properties. Here's my adapters, and so what am I plugged into? I'm plugged in right here. And so I go to my properties here, TCP/IP4. This is obtaining an IP address automatically, all right? Because that's what I'm plugged into. But I'm going to go ahead and plug in my USB to Ethernet adapter here real quick. Hang on a second. I'm going to plug that in. We did this, and you do a lot of that. There it is right there. It just came up. And remember, on this one, I assigned a static IP address to it because I need to talk to this equipment. This is in the network settings of the computer. This is easy to do. When you get a piece of Allen Bradley equipment, there's another piece of software that's kind of doing what I'm doing here. It's called Boot P, or it's RS Links is a way to do it, or Connected Components is a way to do it. It depends on what piece of hardware you've got and what software you're going to do and what it's going to look like. But you're basically doing what I'm doing here. You're giving something a static IP address. This is just the way you do it on a computer. Okay. Yeah, I mean, and like I said, once you get into setting up equipment and everything for your job, and you get to be an internet or Ethernet IP at Wizard, you're going to be a hero to the company. They're going to know about you all over the place because you're going to be the person who can get this stuff talking. But it's a big pain in the butt sometimes getting these dynamic host protocols recognized and then set up. So this goes through and uses connected components. You set these up. Here's another thing. We're not using the lab volt motors. I have there's 56 frame motors there. They're 120 hertz motors, and I put them around, and they're there. Those are the motors that you're using. Be careful with them. You want safety glasses because there's 3-phase. You'll set all your components up. So when it says go and set the motor specifications, it's the marathon motor there. That's what you need to set this drive up for. Okay. And then this goes to talk to you about how you set the drive up and then you upload it. And then finally, when you go on links and you install it, the drive will already have everything on it. Okay. Once you're online with the drive, by the way, you can use Studio to go back in and change the parameters if you want to. Okay, you can. I'm sorry, I missed that. Corey, say that again, would you? It went too fast. Type it again, or hit send again, or copy paste, whatever that was. Corey, I missed it. What was it? Nothing? The drive is you're going to set it for the nameplate of the motor, which I think is 230. Well, you set it for 230, but we have 208 available, and so usually it's 0 to input voltage is what it is. So if you have 208 available, well, typically on a drive, that's what it would be. If we had 460 available, that's what it would be. But these drives are pretty cool. They're a little bit different. I see what you're asking now. These are cool. These are cool little drives. These actually take 115 volts AC line cord. You plug it in, and it's going to make 3-phase out of it, and it'll make. I I don't remember the name, but I think it'll make 230, up to 230 3-phase. So that's good. All right, but that's a good question. I'm glad you brought that up because it's a lot of drives. If you want, 230 volts or 460 volts, a lot of drives are just rated up to 230 on the input, and that's what they'll do, output 0 to 230. Or if you want high voltage, to go 0 to 460. It's kind of one or the other. All right, that you would want a 230 drive or a 460 drive. But these ones, and these are what these hobbyists like, like if you have 3-phase and stuff. 115 generates 3-phase, and then it just goes through here and shows you how to do it. All right, now once you get here, you're going to use the sequencer control. All right, and so what that is this right here, VFD word handouts motor nameplate. Oh, I got it right here. So what we have is, you're going to set this up to be Ethernet IP driven. And so here is the control word that drives this. All right, here's the least significant bits. It's going to be 1110101101010111, whatever. All right, if the least significant bit, there's a 1 here, it's going to be stopped. If there's a 1 here, it's going to be start. So you think that your words are going to be whatever and end with either a 0 1, or they're going to come in here and they're going to end with a 1 0. All right, but you're going to end up with a word here because you're going to drive this sequencer through this right here, 144 RPMs, 1200 RPMs. You're gonna run this for 5 seconds at this speed in the forward direction with this accel and this decel time, and then it stops. All right, and so it's going to come to a complete stop for 2 seconds, and then the next command word, you're going to use a sequencer, is going to get pushed into the drive, and the next command word that does this command word is going to be pushing for 2 seconds. There's going to be 1200 RPMs, reverse, quarter. And how do you get all that? You come here and some combination of 1011010101 matches up to all those properties. And here is the command word. So for each one of these cases right here, excuse me, that's right here. For each one of these cases, you want to write down the 16-bit word, is what I recommend. And then like I said, I like to convert it over to decimal so I can just, pump it into the sequencer. All right. So does that make sense on a scale of 1 to 10 that this is represented by a word? And that's the first part of the sequencer. All right. Next, ready? You actually have to stop the sequencer in order to do the next word. Robert, is that right? Did we get that part working or not? The sequencer has to be given a stop command in order to be given this next position, okay? Which means that you're going to have to come in with a word that's got a 0 here and a 1 there, and whatever else you got here for 2 seconds before you go to the next word here. All right, and then you got to throw in that same word again for 2 seconds. You got to come to a complete stop before you throw in this word. Okay, so it does have to come to it does want a complete stop before it takes the next run word. All right, and then finally you have the analog control to move it 0 to nameplate RPMs. All right, and that's the scaling that we're talking about, and you can get that off the nameplate. So yeah, this is going to be, I don't know, we'll see how it goes. Could be a little involved. So, and that's our last lab. So I've got quiz then lab. So if I stop sharing my screen, and if I look in here, I understand the hard drive medicine. I think I got most of the chat stuff. So once again, another kind of short lecture, a little bit more of an involved lab. Be sure you read over it and that you understand what's going on. I have the quiz open for you, and you can stick around and ask me some questions, or you can go take your quiz. That's what I got for you guys tonight.